In this video, we're going to talk about geolocation. Imagine your smartphone quietly mapping your every move without you giving it instructions or directions. That's the power and the mystery of geolocation data. A digital trail that shows where a device has been. In simple terms, geolocation data is information that ties the device to a physical location. It can come from satellites, from cell towers, Wi-Fi hotspots, Bluetooth beacons, even the IP address on a Wi-Fi network. Essentially, your phone or computer is constantly picking up signals that reveal where that device is. Think of geolocation data as passively collected information that identifies location through GPS, Wi-Fi, cell tower, IP address, or Bluetooth. Whenever you see a map icon, whenever you see that location tracker, that's geolocation data at work. There are many systems that play into geolocation. GPS, the Global Positioning System, uses satellites to pinpoint a device's latitude and longitude. Wi-Fi positioning compares Wi-Fi networks against known databases of hotspots. Cell tower positioning uses signals that your phone exchanges with different cell towers to triangulate the location, to estimate location. Bluetooth beacons, small transmitters that we find in stores or public spaces, can signal when you're very close, often to a few meters. Even your network's IP address can hint at which city or neighborhood you're in. In practice, a cell phone fuses these methods together. If GPS signals are weak indoors, for example, we fall back to Wi-Fi or cell data. If Wi-Fi is sparse, we fall back to satellites. If satellites are sparse, we fall back to data. What this means is that a device can usually report location, often between 5 to 10 meters if we're using GPS, 5 to 20 meters using Wi-Fi, to tens or hundreds of meters using cell towers. So let's talk about a few of these technologies. GPS, for example, uses satellite signals to calculate position. If you're outdoors and it's a clear day, it can be very accurate, often to a few meters. In cities or indoors, for example, accuracy worsens due to signal blockage. Wi-Fi, for example. Wi-Fi knows roughly where nearby routers are. If you're in a dense area with many access points, like a city, for example, Wi-Fi location can be surprisingly accurate, to the order of 5 to 20 meters. If you're in a rural area with fewer networks, it's much rougher, it's much less accurate. Then there's cell towers. Your phone connects to a cell tower in order to make a call, to send a text, to access data. This will leave often a relatively rough footprint. Your phone it'll record which tower your phone connected to. In a city, this might help you narrow down to a few hundred meters. In the countryside, it could be kilometers, depending how many cell towers there are. Bluetooth beacons, the ones that we talked about in the retail environments, Bluetooth beacons are very short range. If your phone is within 10 to 30 meters of a known beacon, it can pinpoint location very accurately, up to 5 meters. This is why retail stores, traffic often use these methods. And then any app. Think of all the apps we have on our smartphones. Any app that you give location permission can collect coordinates and send them back to their company servers. And this often happens in the background without you even needing to open the app or open a map. In short, these modern devices are always listening. Geolocation is the ability to track a device's whereabouts, and it's very easy because almost every person has a smartphone. And these smartphones have radios and sensors, they have the apps that collect this data. And we allow this. Every time we open our map app or weather app or any game or app that we allow location services, our phone is quietly sending this data back. And also, many apps, often for legitimate reasons and others, and sometimes for commercials, send this data to third parties. So let's think about this. Once your device records its own location, what happens to that data? Well, there's an entire industry behind it. Let's think of it this way. Are the device and the operating system, your phone's GPS or Wi-Fi or cell tower will determine a location. It'll save that on the device. For example, if you have Google Maps, for example, and you have the timeline, or any app that you've given permission. And then these apps, these will send the location off device. For example, a weather app might send it to its server, so it can give you a more accurate location. Many apps embed third-party SDKs, software development kits, from location data firms. These SDKs automatically capture location whenever the app is running and send it to a data company. So even if an app's main function isn't mapping, it can still funnel location data to others. And then separately, your mobile carrier, your cell phone provider, knows roughly where your phone is and where it is on their network. Every time you make a call or use data, it connects through a cell tower. These carriers log which towers a device is using. That's how 911, for example, can locate you. These call data records, CDRs, are very coarse, but they're valuable. Analysts can subpoena them. They're another source of location, separate from GPS. Most data ends up in the hands of data brokers and aggregators, legally or not. Companies like OutLogic or Ventel or SafeGraph, many of the others, buy and collect huge volumes of location pings. They aggregate data from many apps and carriers and networks. These brokers then package and resell the data. In industry terms, the raw feed, they're full of latitude and longitudes, they're anonymized and they're processed. In practice, this means that your coordinates and timestamps get mixed into huge tables and data sets, often with just a random device ID, before anyone even looks at them. And then finally, retail, research, government, businesses, they buy this data and they query this location intelligence. Retailers might buy foot traffic analytics to determine how many phones enter a store. Tech companies might buy demographics for advertising insights. Law enforcement and intelligence agencies are also big customers of this data broker information. In the US, the IRS, Customs and Border Protection, the military, and other federal agencies purchase location data from private vendors. This is separate from the legal subpoenas that they make to carriers. They're buying up anonymized location feeds. The key point here is that your phone generates raw signals that travel through multiple hands. The location data process, the market, is vast and it's multi-layered. It starts at your phone and it ends with aggregators and brokers. Think of this whole process as a river. Your phone's GPS and Wi-Fi pings are like drops that flow into streams, apps, and then a lake, a data broker, and eventually out into the faucets that companies and agencies drink from. Along the way, this water is filtered, mixed, or treated, meaning that the final data looks quite differently from when it started. Let's talk about what analysts see versus the raw reality. When you hear location data, an analyst might expect a tidy list of time-stamped places, but that's usually a processed product, not the raw stream from the phone. Think of it like bacon. The raw ingredients are all this sensor data, but the analytical product, that's the final loaf, that's the bread. That's the summarized timeline of maps, of map points and other points. In practice, analysts usually get cleaned or sometimes aggregated data, coming in the form of spreadsheets or GIS files, listing latitudes and longitudes and times. These may be snapped or connected to certain places of interest or roads. If there are outliers, they might be skipped. For example, if raw GPS occasionally jumps several kilometers and glitches, a cleaning step might have removed that outlier. If a device is pinged at the same location dozens of times, The output might say the handset stayed at location between this time and this time, instead of repeating 100 different entries of the same. By contrast, the actual raw generation of that data is much messier and much more dense. A smartphone might record its location every few seconds or whenever it moves. It may record multiple fixes per second with a good signal. All these raw data points, the latitude, longitude, timestamp, device ID, stream out continuously to whoever who's listening. In between this, your phone might also be logging Wi-Fi network scans, Bluetooth network beacons, or cell IDs. Or each of these can give location clues as well. But analysts almost never get that entire data set. What they get is usually a final product after someone's done the heavy lifting. Heavy lifting being removing exact personal identifiers, filling out the nonsense or the glitches, merging duplicates, or even inferring visits and stops or what the data means. For example, one of the data brokers commented that they take that raw feed, they engage in clustering, time filtering, and they add their own context to produce a report. In short, the gap between data creation and data received can be large. An analyst might see one geolocation point labeled device 123 is at Toronto Park at 12:15 p.m. And they might think, oh, well, that device is in Toronto Park at noon. But in reality, that phone might have been pinging its GPS every 10 seconds all morning, only to have the third-party vendor sanitize and clarify and boil it down to that one final coordinate for midday. Or the vendor might have interpolated between morning and afternoon and said the device traveled through Toronto at 12:10, even if there was a 10-minute gap with no pings. What matters here is trust and context. The analyst's inputs may already contain missing pieces or have added assumptions from the source. If we only see the output, we might not know, for example, that in the afternoon that location was inferred rather than directly recorded. We might lose the specific accuracy. We might not see the variables there. When we receive data, it's often polished. It's not necessarily the raw data, and that's something we need to be aware of so that we can interpret the data properly. And there are many limitations and uncertainties when it comes to geolocation data. Location data sounds very precise, but it's full of uncertainty. Every method that we've talked about today has limitations. Accuracy varies. GPS might give you 3 to 10 meters in ideal conditions. But near tall buildings or indoors, it can jump around unpredictably. Wi-Fi positioning depends on having an up-to-date database of routers. If a new router isn't in the database, the location could be off by tens of meters. Cell tower data can be hundreds of meters off, depending how many cell towers there are, the urban versus rural. Even Bluetooth beacons, they only work if you're in a space equipped with them. And then think about timing. Devices don't always record data continuously. If your phone is asleep, or it's in airplane mode, or if it's simply not asking for a fix, there will be blank stretches. One study found that in a voluntary logging setup, over half of the expected hourly location checks were missing. In fact, 63% of the intended hourly positions that were meant to be recorded were absent. This pattern of missing data is non-random. Phones often skip logging at night or when they're indoors. In that particular study, they noted that iPhones recorded far fewer points than Android phones, partly because of the iOS software that refused extra geolocation data to save power. What's the practical effect of this? Someone's timeline might have big blank spaces. An analyst might see no data from 11 p.m. to 7 a.m. We should realize at that point that maybe the phone was turned off or out of service, not that the owner of that handset vanished. Another tricky issue is spoofing and manipulation. Location data can be faked. A user or a malicious app can install a fake GPS utility that tells the phone it's somewhere else. Third-party attackers can jam or replay GPS signals to mislead the tracker. And even at the data level, things can be altered. For example, the GPS coordinates embedded in a photo's EXIF metadata can be edited. The location, the time can be changed. EXIF data can be easily manipulated with the right software. Similarly, timestamps on location logs can be changed. In investigations and analysis, it should be widely known that you can't blindly trust a claimed location without verifying it. Metadata and context need careful checking and analysis. We must also consider the context of movement versus dwell. If a device is in motion, let's say it's riding in a vehicle, it will typically produce a stream of changing coordinates. If it's stationary, you'll get repeated points around the same spot. Analysts often use this to detect dwell time, like how long someone stayed at home or in one particular location. But remember this, if a device stops pinging while it's parked, it's turned off or it's asleep, the analyst might only see 2 points, one where it stopped and one when it starts moving again. Without knowing this, one could think that the person teleported between 2 locations. Conversely, lots of points clustered in one place might suggest dwelling. But it could also happen if someone sat on a bench or if the phone stayed in one place in a room. Interpreting movement versus dwell requires care and ideally supplementary information like timestamps or other auxiliary data to ensure we know what happened. And then finally, let's think about precision versus accuracy. Analysts must remember that coordinates usually have an error circle. A reported point in front of a building might be actually a block away. Without clarity on how accurate the data point is, it's easy to overstate we know exactly where they were or where exactly that device was. For crime analysts, it's important that we understand all of this, because if we treat geolocation data as infallible evidence, as completely true, we'll make mistakes. Think of geolocation data as eyewitness testimony. It's powerful, but it's fallible. It can support and corroborate a story. It can lay down a timeline, but only if we understand the origins and the weakness. Talking about data broking earlier, we've seen that what the analyst sees has often been massaged from the raw input. Why do we care about that? Because misunderstandings, misinterpretations can lead to the wrong conclusion. For example, an analyst might see a device ping near a crime scene and think, aha, the suspect was there. But if the point was actually inferred from an earlier route, or if the device was on a bus or public transport, the story changes. Or consider an app that only logs location when it's opened. If the suspect never opened the app, the log shows nothing. Not because they weren't moving, but because the app didn't record or didn't sample the location. An analyst who doesn't know this could mistakenly declare no movement equals an alibi, when in reality it's no sampling, there's no data. Understanding this data pipeline also protects against trusting a final report too literally. If we know the data came through an app, if we know it came through a specific SDK, we can ask, what is the sampling rate? How often does that data get monitored? If a point seems out of nowhere, we might wonder if there was an error, if there was an issue or a bounce. If the data has already been aggregated and anonymized, we might note that the personal context, who does the phone belong to, is lost. So it's more of a puzzle than a confession. Indeed, geolocation data is so fraught with these pitfalls that forensic teams emphasize protocols and cross-checking. Just like we wouldn't rely on a single fingerprint, we don't rely on a single data point. In practical terms, knowing the difference between raw and final data affects how we present findings and what questions we ask. When mapping a suspect's route, we should remember to depict any uncertainty. If there are if there are certain cell towers, for example, that have a wider range than others. When timing movements, we want to watch out for gaps and leaps. If a phone is only reporting once per hour, we can't comment on what has occurred during that time period. And if the data is being provided by a third-party commercial vendor, we should understand that that data may already have been massaged. It might be a different reality. In summary, in conclusion, geolocation tracking is very powerful, but it's complex. Nothing happens without context. By understanding how data was collected, who collected them, and how they were processed, we can treat the data wisely. We can treat the data with the respect it deserves. The raw signals are rarely seen by us as the end user, but we get a polished story at the end. Knowing that there's a gap between the story and the raw data, that keeps our analysis accurate and our conclusions sound.